So before moving on to explore this duality which we mentioned before moving on to explore how the frequency and the time domains are connected, in a sense, how they're dual to each other, let's look very briefly at the, if you like, at the differences and the similarities between Fourier series and Fourier transform. So let's try to do this transition from series to transformation and look at why it's natural and why it's even more natural to look at transformations than series. So originally what we had exactly in the periodic function case is that this periodic function could be represented by a discrete number of sine functions. So it could be represented by as a combination of sine functions. So some sine function of a given frequency plus another one, and so on and so on. And this is represented by an infinite sum which went over an index which labeled all of the frequencies. So we had a discrete number of frequencies which were all an integer number of some initial original frequency which depended on the period itself. And so we had omega n, and this n was the label which was going through the integer number. So we had omega 1, omega 2, omega 3, and omega 0 of course was the zero frequency, so the constant term. And this sum actually represented the combination of sine waves, if you like, the interference of sine waves, in such a way that they create a general periodic signal. And to find each of these constants, after translating in a symmetrical about the origin interval, we had to evaluate an integral throughout the whole period. So from minus the period divided by 2 to plus the period divided by 2 of the function itself. And we saw in the previous sections that the two are uniquely related. So if we had the function itself, we could uniquely determine the constant Cn, and vice versa. If we had the constants Cn, we could immediately determine the function itself. So we saw this with the sawtooth impulse, the sawtooth signal, which is a periodic signal, and we saw that the two are uniquely related, and we hinted at this duality. But what happens if we go to the non-periodic signal, which we did just now? So looking at the general function, as we said, the sum we had, so summing from minus infinity to plus infinity over the integer enumerable frequencies, omega n, we now have an integral. So now we're not summing, we don't have integer labeled frequencies, we don't have discrete frequencies, we have a continuum. So we have the full spectrum, and we integrate from minus infinity to plus infinity. Because you may be wondering, how are there negative frequencies? This does not mean that the wave itself has a negative frequency. The interpretation is simply the sign of the constant. Since a complex function, as we saw, depending on the sign of the exponential, we're going to have a different sign in front of the sine function. So we're going to have plus or a minus in front of the sine function. And looking at how we generalize the sum into an integral, and how we generalize the integral which gives us the constants into a new function, we note that essentially what we have done is we have taken the limit of having infinitely many frequencies infinitely closely packed. So we don't have a discrete number of constants, Cn, which depend on a discrete number of frequencies, omega n, but we have a function, f capital if you like, which corresponds on the frequency itself, which is now a continuum, so omega. And these things, so f of t and f capital of omega, are the two functions in the two domains. So if f of t was our original impulse, if it was our original time-valued function, we call it the function in the time domain, obviously, and its capital, the capital F, or its Fourier transform, we're going to call it the frequency domain function. So the two are once again connected, and we're going to see that each of them is enough to determine the other. So the two uniquely determine each other without ambiguity. And if we had f small of t, we could immediately compute f large of omega, and vice versa. Just to mention generally, since in radio electronics we may be used to working with the natural frequency, or with nu as we label it, 1 over the period, it's very easy to convert to that as well. Since in fact the first integral, which is integration about all of the angular frequencies, if we interchange the angular frequency for the regular frequency, in fact this twice pi norming constant drops. Now one important note here which we might actually want to make is also that you should not be scared by this twice pi norming constant and where it comes from. it comes from the mathematical results. So if we formally do this transition from discrete to continuous frequencies, we're going to get this factor simply because of the requirement that when we do the transform and then the inverse transform, we should get back at the same function. So, continuing on and looking at duality at this point, we're going to look at a very concrete example just to get a sense of what it means to have this frequency-time duality. So, the very simple example which we started with, or the very simple impulse which we started with, was the rectangular impulse, the rectangular non-periodic function. So it simply has some constant value, so let's take it as being 1, within the origin, so from -1 to +1, as we're going to put it, it has the value of 1, and everywhere outside of this it's simply 0. So this is what you may think of as something being off all eternity, then turned on for just 2 seconds if you like, so from -1 to +1, and then being off again. Just a very time-limited disturbance. And what this leads to, so if we take the Fourier transform, the scary-looking infinities in the integral, they're gone, because outside of this domain where the function is 1, the integral is equivalently 0, so the integral from -infinity to +infinity, it turns into simply an integral from -1 to +1, and the function is simply 1 in that domain. So integrating the exponent is very easy. And doing this, we actually get the result up to a constant of a sine function divided by its argument. So we get sine omega divided by omega to be the frequency domain representation of this rectangular impulse. So what does this mean? Well, if you look at the plot, it tells us that this central region around the 0th frequency is the highest in terms of, you may think of contribution, in terms of amplitude. And you see that the further we go to the higher frequencies, the lower the contribution is. In fact, some contributions have negative amplitude contributions, but this is not very important for our case. What is important to note is that the central region is close to the middle. Now, what happens if we tried to represent a periodic square signal? So actually what we started from, if we took the same signal and gave it a period in such a way that we actually want to look at a periodic sequence of rectangular pulses. Well, what we get if we represent again the Fourier series at this point, what we get is a discrete dependence between the nth constant and the nth angular frequency, but it has exactly the same shape as that which we had for the Fourier transformation. There is an additional period which appears, but this actually goes away if we take the limit of t tending to infinity. So what we learn is that essentially that the Fourier series is a special case of the Fourier transform when our signal is periodic, but a general signal, a non-periodic signal, it requires not only an infinite number of sine waves to be represented, it requires a non-enumerable number of sine waves. So if we had a periodic signal, we still have infinitely many frequencies, but they're still enumerable, so we can label them. Omega 1, omega 2, 3, 4, and so on. We can label each one and we can say this one is larger than that one. But if we have a non-periodic signal, then there is no labeling because we have a whole continuum of frequencies which need to be merged. And instead of summing, we're integrating now. So you can look at the integral as a type of continuous sum. So we're summing, but not by a discrete index, but by a continuum. And if we look at what happens when we keep increasing the period of this original rectangular periodic function, we see that more and more frequencies pop up. On the first image, we start with a small period, which is actually the size of the impulse itself. And we see that we have a few frequencies. They're evenly spaced, of course. They follow the same functional dependence as the Fourier transformation, which is shown in red. But as we move to the next images, you see that we're actually increasing the period more and more. And increasing the period, it means that we're getting all of the squares, all of the rectangles further apart, and we get more and more spectral components. We get more and more frequencies, and with each doubling of the period, we actually get double as many frequencies. So more and more frequencies. And what happens in the last image is we have actually taken so many frequencies, so we've made the period so large that you can barely see distance between the frequencies. And so this is a graphical representation of what we said about taking the limit. So what we've shown here graphically is how that same limit of increasing the period, how it looks in the Fourier domain or in the frequency domain, And you can see that it actually corresponds to the fact that we have taken more and more frequencies and we have taken them to be more and more densely packed. So we have gone from discrete number of frequencies into a continuous number of frequencies again. So once more, Fourier series represents periodic signals, and periodic signals need only a discrete number of frequencies, while Fourier transformation describes general signals and generally requires a continuum of frequencies, the whole spectrum. Now, one important quantity, which is quite useful in many cases, is the energy of the signal. So if we had, for example, an electromagnetic wave, we saw earlier on that the square of the amplitude of the electric field or of the magnetic field represents, up to some constants, the energy that it carries. Well, for a general signal, we may not have the same meaning behind energy, but we can define a similar generalized energy, which does not have to be dimensionful, so it may not have the dimensionality of joules, but the square of the amplitude of the signal itself actually gives us some quantity of how much energy it carries. In fact, the square of the amplitude tells us how much power it carries, which can be seen as energy density over time. And if we integrate over all of the time in which the signal was present, then integrating power over time, it tells us exactly how much energy the signal carried. For example, of the rectangular impulse, in the beginning, when the signal is just zero, it has no energy at all, but when it goes up, for the duration of the square impulse or of the rectangular impulse, it carries some energy, and if we integrate, so if we multiply by the time in which we have amplitude, by the amplitude squared, we're actually going to get some measure of how much energy has traversed in total. And this idea, this definition, is very useful, and it tells us that we can actually get the full energy by integrating over the full time period of the signal, the square of the amplitude of the signal. Now, one very important result, which actually shows the most important consequence of the frequency-time duality, is Parseval's theorem. And Parseval's theorem states that this function which we formed in the time domain, so the amplitude of the signal squared, if we integrate it over all of time, we said this is total energy, Parseval's theorem tells us that this total energy is exactly equal to the same definition in the frequency domain. So instead of the signal squared, if we took the Fourier component of the signal, so if we took the dual component or the frequency domain of the signal squared, and if we integrated over the same, but this time in frequency, so from minus infinity to plus infinity of all the frequencies, we would get the same result. So it tells us that, if you like, the energy density in time, power, is equivalent to the energy density in frequency. And this Fourier component squared, so the Fourier transformation of our initial signal, its absolute value, of course, because it may be a complex function generally, its absolute value squared has the interpretation as spectral energy density. And why do we call it that? Because it's energy density over the spectrum. So if you integrate over the full spectrum, all frequencies, this quantity, you're going to get the total energy. But for each specific frequency, the value of the spectral energy density actually tells us how much it contributes. So how much this specific frequency contributes, depending on its amplitude in the signal, to the final shape or the final energy of the whole thing. And just to give an example of what this looks like, let's consider, again, our rectangular impulse. Let's consider what happens if we restrict its spectrum. So if we look at how this function, the spectral energy density function, looks, we can see that it has a maximum near zero, absolute maximum, at zero exactly. And we can see that the majority of the function is actually very close around the origin. So in the interval from -6 to +6, we have roughly 95% of the total power if we integrate in this interval. So since 95% is quite a lot, it's almost 100, we can actually tell that the majority of the information for the signal, the majority of the shape, if you like, is carried within this part of the spectrum. But what happens if we cut all of the higher frequencies? Well, we can see that on the right, the result of cutting anything higher than 6 in terms of angular frequency is actually some modification of the original signal. So if we took the Fourier transform of our rectangular impulse, we got it in the frequency domain, and then we cut some of the frequencies off and tried to reconstruct our rectangular signal, what we get is this, you can see, fluctuating results. So this is what is called aliasing, and you can see that it follows the rectangle, it very closely resembles it, but it's not exactly one-to-one. So in some points it's more, in some points it's less. If we average this result, this aliased result, we're going to get something very close to the original rectangular impulse, but generally there are modifications. So this tells us something very important that we need to keep in mind. It gives us a general lesson about working with continuous spectrum. And this is the fact that no machine can actually work with the continuous spectrum. So we will always be forced to cut some frequencies out. First of all, no machine can actually produce all of the frequencies contained in the spectrum. There are super high frequencies or super low frequencies which we cannot generally produce easily. And so if we want to form a general signal, first of all, we cannot physically get to all the frequencies to make it perfect. And second of all, we do not have this infinite bandwidth since, as we spoke earlier, only certain portions of the spectrum are used for different things. And so in reality, when modulating and when encoding and transmitting, we're going to use only part of a spectrum, and we're going to see and use Fourier analysis to actually get what we need in order to get a good enough result. But this thing that happens if we cut parts of the spectrum that we actually need to form a signal, this aliasing might be a problem in some cases, and in some cases if we have not considered our bandwidth well enough, it will lead to problems. So it's something very important to keep in mind. And the spectral energy density is something very important as a concept, which again shows how central to communication and to physics in general this frequency to time duality is.